means they produce more electricity when the sun is shining directly on them. Produce as a tracking signal. You can write out clicking the Simulink button examples. And Simulink models are built up from blocks and signals. To model the equation for the panel, we'll start with the integrator block. Let's click and drag an integrator from the library into our model. So why an integrator block? Well, the integrator block takes an input and integrates it over time. If we integrate acceleration, we get velocity. And if we integrate velocity, we get position. This is the basis for modeling differential equations in Simulink. Our equation has acceleration by clicking and dragging between blocks. Don't worry about these red lines. We'll connect them up in a second. It's a good idea to label signals to keep things organized. So we'll double-click the signals and type a name. Let's name this one theta dot dot for acceleration, then theta dot for velocity, and theta for the position of the panel. Next, let's model the right-hand side of this equation. First, the torque term. Let's use a constant block. We'll replace this with the motor later. You can double-click a block to change its parameters. Let's change the value to 10. We need to perform a subtraction, so let's also grab a subtract block. The damping term depends on the panel's velocity, the theta dot signal. We can branch this signal by right-clicking and dragging to connect it to the subtract block. And don't forget, we still need to multiply that by kd. Let's use a gain block for that. Rather than hard-coding the gain value, we can also use a variable or even Matlab code. So let's just say the gain is kd. That red box is telling us that kd hasn't been defined yet, so click the 3 dots and select Create. We'll give it a value of 5 and store it in Matlab. The variable kd j. We'll do that with another gain block. But now we know the name of the block, so we can just double-click in the model and start typing the block name. We'll set the gain to 1 over j, and again, let's define the variable j in the base workspace with a value of 8.6. Let's add an annotation to show the equation being modeled. So that should be all we need to model the panel, but to check if everything is working correctly, we'll want to visualize some signals. Simulink has a bunch of and connect it to the signal we want to view. We're ready to simulate the model. We can set the simulation stop time in the Simulation tab, but we'll leave it as 10 for simulation finished, but what you didn't see was that Simulink numerically solved the differential equation through time. Double-click on a scope to check out what happened. In the position, the velocity starts from 0 and levels rotating it. See what happens if we rerun, and that looks good. We see the panel now spins in the opposite direction. Now that we have the panel model working, let's group those blocks together to keep things scopes out. All those blocks are contained within this. Double-click. Go back up to the top level. A motor.
就去过。
torque and move the panel. Let's check what happens. We can see that the panel spins when a voltage is applied to the motor. So everything looks good so far. Okay, we've modeled the panel. The sun is over. The panel. Have the position of the panel. We'll use a unit step input. That's pretty common in control design. We'll test it with some actual sun position data later. Now to calculate the error. We'll use a sum block. It's already got this nice circular set of options, but a common approach is some form of because the control. We connect the input.
Not far out of the times, just like another season. Maybe the sun with you with me. No reason for the cherish every day. Selling from my rainy season.
Input to the error. Error signal, and to customize the controller, we'll switch to a PI controller. The D term helps respond to quick changes, which we don't need because the sun moves steadily across the sky. There are two gains to adjust, one for the proportional term and one for the integral term. These affect the controller's response. We'll set the proportional gain to 240 and the integral gain to 180. To see how well the controller performs, let's use the same scope to show both the sun position and the panel position. Notice that a new port is automatically added. Let's run the model and add a legend to the scope so we can tell the signals apart. Let's also make the position line dashed. We can see that the controller shoots a little, then settles to the reference value of 1. That's good enough for our application. Okay, we designed our controller, but can it actually track the movement of the sun? Well, let's see how it performs when we provide it with some real data. Let's load some sun position data into the Matlab base workspace. This file has two variables, a vector for time spanning 15 hours and a vector of the sun's position at each point in time. Let's plot it.
The story cross with it was started. You can answer my life just like a mercy. Not for don't touch the time, so don't see that. Maybe
You can see northwest into the model by replacing the step block with an import. We need to select which data to use. Click Model Settings in the Modeling tab, then navigate to the Data Import-Export pane. There are a lot of settings in here. If you're ever unsure about anything, just right-click and select What's this? This column should always be time. After that, you can add a column vector for each import in your model. Since we now have 15 hours of data, we'll change the simulation stop time. Let's run the model, and we can see it's tracking the sun's position quite well.
people changing.
So we modeled our solar panels